All right, so good morning, everybody. Thanks for coming. It's my first time to actually teach online. I wasn't teaching this last semester, so please be patient with me in case something goes wrong, but please also just go into the chat to ask questions or let me know if I have to speed up or slow down, because this is a session for you. So let me know if the speed's not right. So statistical foundations, lots of fireworks. I know it's not quite July 4th yet, but hopefully those fireworks are more like your synapses going off in the back of your brain to make all these connections between things that you already know and are hopefully already familiar with. Because when you think about all of the topics that we're going to cover, this is really like a course from 0 to predictions in 8 hours. So what could possibly go wrong, really? So when we came up with this, I'm aware that this is a very, very strong day for you guys. So the idea really is that I'm only connecting to things that you already know, and hopefully that way we can build a foundation that you can rely on when you come to the pieces on day 2, like models and predictions. So today we're mostly going to talk about probability, and that is going to be probably a little bit less related to what you are doing with the projects at the moment. But all of these later elements like confidence interval, prediction intervals, models,
You're into your computer.
that's going to...
You're just gonna watch it?
Is this R?
No, it's not R, it's the statistical foundations. We will get into R a little bit. So what?
So sorry, Heike, I was having a conversation with somebody as they're walking by.
Okay.
Thanks.
So what we're going to do is we're going to have a look at the theoretical foundations. And we have a lot of understanding on how probabilities and how chance, how likelihoods work in our regular life. But sometimes those intuitions break down. And at that point, we need to get into mathematical notations to help us over those hurdles. So let's do a really quick exercise. Let's have sort of a survey about the probability that at least 2 of us in this chat share the same birthday. So last time I checked, we were about 53 participants. So what do you think that the 53 of us share the same, that at least one pair of us shares the same birthday? So just the day, not the year. So the problem is I don't want really to collect any kind of private information about your birthdays. Instead, let's phrase this problem as, let's pick our favorite number between 1 and 366. In case you want to get to your birthday, you can use this line of code in R where you substitute the MM and the DD with your month and the day of the month that your birthday is, or your favorite day of the year. And then let's go to menti.com, use this code 956149. There's going to be 2 questions. The first question is, how likely do you think that among the 53 of us, there's going to be at least one pair that shares the same birthday? And the second one is submit your favorite number. Then we'll have a look at the results in a minute or so. Menti is working hard for this. Good, that means we've got some results. Okay. So you can see here, we've got just a slider with records, and here we've got, I guess the average is 147.5, which makes so much sense. But we've got several pairs. So we've got a pair here, and then earlier in the year, we've got another at least 2 pairs that I can see. So let's see whether this comes as a surprise to you or not. I was also asking about how likely do you think is it that 2 people in this class share the same birthday? And this does not come as a surprise to you. Maybe it is? No? 3? Numbers are coming in, and it seems that you are familiar with this particular problem. I guess I'm done teaching that. All right, it's a very strong indication that you guys already know what I'm talking about. That's fine. So this is mostly a refresher. That means you're all super well prepared. Okay, let me get back to the slides. Okay, so connecting to what we already know, what we want to do is the material is chunked into conceptual overviews. Then we'll usually do an example, and at some point I'll ask you to do some activities. In case you're getting lost, or in case you want to follow along, all of the material, so the PDF and all of the code that I'll show, are available from GitHub. So navigate to this page and download the materials. I'll give you a couple moments, and I'll also put the website into the chat so you can read it. You don't have to type it.
I got.
Yeah.
I'll add the link. It's okay.
Thank you. Okay, so what are we going to talk about? I want to just quickly look at probabilities. Then we'll talk about what random variables are. We'll have a look at 2 special distributions that I'm sure all of you are going to encounter for all of your projects. We'll look at how we can describe relationships between random variables, and then we'll have a look at the central limit theorem and why it's really, really nice to have the central limit theorem together with the normal distribution. Okay, so probabilities. We can go and ask our friend Google what probabilities are about. So probabilities, or probability is. I was really surprised when I saw these results because I thought it would be completely arbitrary. What I found funny is that in their in the Google probability is they report predictions, and inappropriate predictions obviously should be removed. So the only ones that I can find here are probability is the Quizlet, and probability is defined as Quizlet. I have no idea what they mean by that, so let's get rid of them. But the other ones are actually quite good, and probability, we'll have a look at each one of these. So probability is another word for chance, yes. Probability is a measure of how likely it is that an event occurs. Probability is always between 0 and 1. And maybe the most important piece in this whole list is probability is defined. So that means that probability is a concept that somebody has defined for us. It's a concept that helps us to understand the pieces that helps us to understand the real world and describe the real world events that we see in the real world using this concept of probability. So that means we'll have to go through a couple of definitions before we can actually do something. So let's get started with this. A random experiment. So we know physical experiments. A physical experiment would be one where things are always going as expected. So there's one outcome. The difference to a random experiment is here we don't have a deterministic outcome, but what we do know is we've got a set of possible outcomes. So this set is called the sample space, and we'll call the sample space omega. So the omega is a set where we include all the possible outcomes. And now we're going to look at subsets of the sample space. And those subsets are called an event. So an event is a set of possible outcomes. And if the outcome of a random experiment is one of the elements in this event E, we say that the event E has occurred. So let's do one of those typical experiments. We roll a 6-sided die. By definition, we don't have a single outcome. So, but we have so this is a random experiment. We have a sample space, so one of the 6 faces will be at the top once this die has stopped rolling, and we'll leave out all of these things that will be on a corner, or the die falls into a hole and we don't have an outcome. So let's assume that that our experiment in itself is going correctly, and that we'll define that to be an outcome between 1 and 6. And now we can define possible events, like we rolled a 6. We'll define that as the subset E of that consists of just the 6. Similarly, we can roll an odd number, so 1, 3, 5, or roll a number that's higher than 2. That would be the event 3, 4, 5, 6. Okay, so that's a random experiment. So we're going to deal with events quite a bit. So let's have a look at how events are connected to each other. So what are the relationships between events? So let's say we've got 2 events. Then we can have a look at how these events relate to each other. Those events can have something in common, and we would call that something in common the intersection of events A and B. So the intersection of A and B are all of those events that are both in event A and in event B, if we think of those events as sets. So this is called a logical and we'll denote this by this cap, so upside down, like we're constraining something. We're catching everything that's both in events A and in event B. Sort of the opposite is we can be very open, and we have this cap, and we're looking at this union, the union of events A and B. That's all elements that are in A, in B, or in both. So that's called the logical OR. And I'm saying logical and logical OR here because, oh, come on. Sorry about that. There we go. I'm saying logical and logical OR here because in day-to-day language, we might not use and OR in the same way. So for example, when somebody asks you what you like to eat and you say, well, I like pizza and I like ice cream, you probably don't mean a logical or a logical and. You don't mean that you like pizza and ice cream at the same time, but you like both ice cream and pizza. So that's probably more like a logical or. So we've got a set A or an event A. And sometimes we need to refer to things that are not in the set A. That is called the complement of A or complement of the event A. And that is everything else that's in the sample space omega, but not in A. So the notation for this not A is, there's different ways that people use. We can sometimes see an exclamation mark or this strange bracket or line with the dip at the end. Sometimes people put a bar on top of A to say not, but I'm not going to do that today because I don't want to get you confused with averages later on. So we'll use exclamation mark or this, this drop-off line as not A. And a last definition for right now, we'll call A and B disjoint if they don't have anything in common. So there's no elements, and the no elements symbol is this struck through 0, and that struck through 0 is the empty set. And it will denote that A and B are disjoint. So disjoint means nothing in common. Okay, so I'll hand over to you, your turn. Instead of just a single roll of the die, we've got 2 rolls of the die. So assume that you've got a red die and a yellow die. You roll both die and you write down the result in form of this tuple, red die, yellow die. So we've got a random experiment, and I would like you to write out the sample space, define 3 events, A, B, and C, and then have a look at the intersection of these samples. In the intersection of those events. So I'll give you, let's say, 3 minutes to work through this, and then we'll come back to this. Okay, that wasn't, oops, that was my timer. Okay, so do we have any disjoint events? You can actually respond. And if you respond, please unmute yourself first or write in the chat. A and B are disjoint? Yes, you're right, Jessie. A and C. I'm not sure about A and C. Okay. That's okay. So let's have a look at the solution. Okay, I think you're all on top of this. Real quick solution. In case you're completely lost, you can have a look at the PDF and go back afterwards. So oftentimes it's a really good idea when you're stuck in a problem, or if a problem seems complicated, to really write out the sample space. So sample space of rolling 2 dice. And here, because one is red and one is yellow, they're distinguishable. So we've got our omega, and we start out and write this whole matrix with red die shows a 1, shows a 2, a 3, and so on. And then in each column, we would have the yellow die change the face. So a 1, a 2, a 3. So that gives us a total of 36 elements. And if you think this, writing this out is a pain, I'm completely with you. So a much more concise way of writing this out would be to write this out as the set of all tuples I and j, where I is between 1 and 6 and j is between 1 and 6. And then we can have a look at 6 combinations here for I, 6 combinations here for j. Multiply I and those number of combinations 6 by 6, and we get the same numbers here. So now we can write out the events as a subset. So A is the event that the sum of the 2 dice is 7. And we can go through this list. 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, 6, 1. That would be event A. B is the event that both dice show the same face. So yeah, that's the 1s, the 2s, the 3s, and so on. And C is the event that the red die shows a 2. So that's just the second row in our matrix. It's an accident that all of these events have a length, or have 6 elements, a length of 6. That's obviously not necessarily the case. So B and C, looking at the elements that both have in common, that would be 2 2s. A and C, like Sophia said, 2 and 5. A and C are not disjoint. B and C are not disjoint. But if we have a look at A, B, and C, that's the empty set, and they are disjoint. I'm missing here A and B, and they are disjoint because obviously we can't reach a 7 because 3.5 is not one of our faces. All right. So this is one of these solutions. I've tried to write out the solutions in a lot of detail. I'm not planning on going in as much detail over every single solution, but if you want me, please, please let me know in the chat, and then I'll slow down for that. Okay, so I think we're ready to actually define probabilities, and the definition of the axioms for probabilities. That definition goes back to Kolmogorov. So he's featured here. And the 3 items here are called the Kolmogorov axioms. So axioms mean that these are definitions, these are assumptions that we need to rely on. There's no way of proving any of this. So it's like the assumption that the shortest distance between 2 points is a straight line. That is also an axiom. So similarly, we have 3 axioms for probabilities. So we define that for any event A, the probability for this event is going to be between 0 and 1. And I think it's easy to understand why this is a definition. We could have just as well said between 0 and 100, between 2 and 3, but we define a probability to be between 0 and 1. And then we sometimes talk about percent, so obviously we just multiply any probability that we get out of here by 100 to get the percent. Second one, the probability for the whole sample space. So the sample space itself is also an event. So the probability for the whole sample space is equal to 1. So I alluded to that before with a single roll. We excluded all of the possibilities in which we can't come up with a result because the die is eaten by by a dog. So we are not going to consider that a successful experiment. So for a successful experiment, we will assume that the probability that one of the elements in the sample space is a result is equal to 1. And then maybe the most important definition here is if we have disjoint events, A and B, so disjoint, remember, the intersection of A and B is 0. A and B do not have any elements in common. If that's the case, then the probability for the union of these two events is just the sum of the probability of each individual event. So P of A plus P of B is equal to the union of those probabilities. So what can we do with these? Based on this, we can prove all kinds of different properties. And I'm going to spare you the actual proofs, but what we can say is that if we have those 3 properties or 3 axioms, we can derive that the empty set has a probability of 0. And I hope that makes intuitively sense. So if we don't have an event, or if we don't have an outcome, then the probability for that should be 0. The probability for the complement of an event is nothing but 1 minus the probability for the event. And also very important, if there's 2 events, just any event, so we're not considering that they have to be disjoint. If there's 2 events, then the probability for the union of these events is the probability of A plus the probability of B, and we'd be done if these events were disjoint. But for regular events, we have to subtract the probability of their intersection. So that's relatively easy to understand if we think of the probability as being equal to the area of each event. So if you think of the probability of A as being equal to the area of A, then the size of this ellipse is the probability for A. Now, the union of A and B is this butterfly-shaped thing. And by adding the probability of A and the probability of B, we've now added the probability of their intersection twice. So in order to get a proper estimate for the area or the probability of the area, we need to get rid of the intersection here in the middle. And we subtract the probability of A and B. So we only want to count this once. And that would be the way, this is the formula to do that. So general events will just add up as long as we count their intersection only once, so we have to subtract their intersection. Okay, so once we have probabilities, we now know how to calculate with probabilities. So essentially, the Kolmogorov axioms give us a way to do calculus with probabilities. So how do we assign probabilities? And that's a really deep question. Sometimes we know, so we have a theoretical model from which we can derive probabilities. and sometimes we have estimates. So we have data that we've observed and that will inform us how to come up with probabilities so that they are consistent within each other. So for a fair die, we assume that all sides come up with equal chance. We've got our sample space and we just define, or we say the die is fair if all of the outcomes, all of these individual outcomes have the same chance. So 1 in 6. Here's another example. So national pet owner, there's a survey on that. And from the 2019 survey, we have the following breakdown: the number of US households that own a pet. So there's 42.7 million US households with a cat, 63.4 million households with a dog. And from just these two numbers, we see that these 8 pieces are, these 8 elements are not disjoint. There's a lot of households that have that have more than just one pet. So overall, the number of US households that own a pet is about 85 million. So you can see that lots of households have more than just one animal. But we can still, so by dividing by this 85 million, we can still come up with a frequency that tells us something about the probability that if we sample a random US household in which we know that there's a pet, then we have a chance of 5.7 over 85 million that this pet is a bird. Okay, I'll turn over to you again. Let's say we've got a box with 8 identical looking AA batteries, and somebody tells you that one of these batteries is dead. So we have some prior information. So you want to charge the Energizer Bunny and it needs a new battery. So when we randomly pick a battery, what's the probability that the bunny will start up? And how does that probability change if the bunny actually needs 2 batteries? I'll give you a couple minutes again, and then we'll compare results. What's the probability that the bunny starts up if it just needs a single battery? Let's have a look at our sampling space. We've got 8 batteries, and the problem is that at first they're indistinguishable. So to make our job easier, we basically put little stickers on it, and we label those stickers 1 through 8, and that gives us 8 different outcomes, B1 through B8. So let's assume that B8 is defect. It doesn't really matter which one because they were indistinguishable. So let's assume that B8 is defect. And that means that we have a 1 in 8 chance to pick B8. Or in other words, we've got 7 chances that the bunny will work if we pick batteries 1 through B7. So the bunny works with a probability of 7 in 8 or 0.875. Okay, so what about 2 batteries? So there's various different ways that we can set up a sample space. And essentially it doesn't really matter which sample space you pick. Some sample spaces might just be a little bit easier to work with. But if you pick a sample space and you just stick with your sample space, you will get to the same answer regardless of the sample space. So here I'm using a sample space, omega, where I'm again looking at the tuples. So I'm looking at battery 1, battery 2, battery 1, and battery 3, up to battery 8 and battery 7. So how many different elements do I have in this? I've got 8 possibilities to pick the first battery, and then there's only 7 batteries left. So I've got another 7 possibilities to pick another battery, which means overall I've got 56, so 8 times 7 possibilities to pick this battery. So what's the probability that the bunny works? I can't pick the battery 8 in any circumstance. So I've got 7 batteries to pick from in my first pick. And then I've got 6 batteries to pick from in my second pick, because I'm trying to avoid battery 8. So that gives me 42 in over 56, or a chance of 6 in 7 that when I'm picking 2 random batteries, the bunny will work. Does that make sense? Okay, very good. Nice. Okay, so generally, in this scenario, all of these elements can be picked with equal chance. And that means that if we have an event, we just have to pick out all of the elements, and we just have to count the elements, the number of elements, and that is going to give us the probability. So we divide the number of elements in the event by the number of elements overall, and that's the probability for that event. So this is true whenever all elements in the sample space are equally likely to be selected. And usually you can detect that that's the case when somebody phrases a question like, I'm randomly selecting some person from the street. So that's probably, so if we're in the US, we've got 300 million people. So the probability to select one person would be 1 in 300, and every single person in the US would be 1 element in that sample space. So random sampling is usually indicating that the elements in that sample space are equally likely. And you've already seen that we're doing a lot of enumerations. So usually the computer is much better at keeping track of these kind of enumerations and lists. So we can make use of some R code. So the function sample. So sample has parameters x, size, and then these 2 guys here, replace equals false and prop equals null. Let's ignore those for right now. So x means we want to sample a number, x number of elements from a sample space of size. And there's 2 different ways that we can think of this. So that's what this replace means here. We can either pick something and put it back. That would be replace equals true. Or we can pick and not put it back like we did with the batteries. So getting a sample of size X and size are actually the opposite of what I just said. I'm really sorry. X is the number of elements in our sampling space. So that would be the batteries. So 8 batteries. We pick 2 batteries. So we draw size many without replacement. That will give us a list of the number of which batteries we picked in a single draw. If we roll a dice, we are not keeping the face. So you can think of the face going back onto the die. So we're replacing we use replace equals true. And in that case, sample of 6 and 2 would mean that we roll a 6-sided die twice. So here we're just saying 6-sided die. Is that die fair or not? That's what this probability is telling us. So by default, prop is the probabilities for each element in X is the same. So it's an equally likely element sample space. And you can see here, so sample 6, 2, replace equals true is, we're rolling a die twice. Sample 6, 7, we roll a single die 7 times, and we've got some outcomes here. I'm going to turn over again to you, and this is a slightly bigger your turn, so I'll give you minutes for this. Let's quickly talk through this. So we've got a board game, and I hope that some of you at least know the board game Risk. So you're essentially going for world domination using dice. And that means that sometimes a player attacks an area that another player defends. So we've got, let's assume that an attacker uses 3 dice, and the defender can then use another 3 dice to defend. So let's assume that we've got this situation. The attacker rolled 2 4s and a 1. The defender rolled a 5, a 2, and a 1. Those 2 sets of dice are being lined up and then compared. And from the top, the attacker wins only then if her die dominates the defender's die. So in this lineup, the defender wins. In this second line, the attacker would win. In this third line, the defender wins again, because the one, this attacker's one does not dominate the defender's one, and the defender wins. So this means that the attacker wins 1, the defender wins 2. And what I would like you to do is, I would like you to write a function, attack 3, that simulates an attack with 3 dice and just returns the difference in the number of won and lost dice for the attacker. So in this case here that we're describing, that would be 1 loss, so a -1 for the result of this attack 3 function. So once you've got this function, you can use the function replicate to simulate 100 attacks. And that's going to give us a probability that the attacker wins or loses more dice than the defender. So essentially what the attacker wants is to take over and that a country or an area, and that means that the attacker has to get rid of all of the defender's dice, and he will only get rid of them if she can take over all of the defender's dice. You ready? 10 minutes? Okay, really close, okay. Okay, so let's just walk through the code. And this is just one solution. The thing about R is there can be a ton of different ways to get to the same or similar results. So this is just the solution that made sense to me when I was typing things out and I tried to think about how I would approach this problem. So we've got attack 3 defined as a function. And we have to have 3 dice rolled by the attacker. That's this sample 6, 3. So 3 replace equals true. 3 rolls of a 6-sided fair die. And we sort those in decreasing order. So if it's a 2, a 5, and a 3, that would then be ordered as 5, 3, and 2. Then we've got the defender, and the defender also rolls 3 dice in decreasing order. And now we're comparing the attacker's dice to the defender's dice. Attacker greater than defender, that would mean the attacker wins. And so here we've got a vector comparison. So we do an element by element comparison. We look at the outcomes will be 0s or 1s. 0 if the statement is not true, 1 if the statement is true. So we can sum over those 0s and 1s, and that gives us the number of wins. Similarly, the other way around, attacker is less than or equal to the defender. We sum over that, that gives us the number of losses. So we could just double check that wins and losses, if we add those, will always be 3s. That would be a good check here to do, to see that the function is actually doing what we want it to do. And we can report a final result as the number of wins minus the number of losses. That's what this attack 3 function was supposed to be doing. And now we run this function n times. So here n is 100, but you could set it to 5,000 or 50,000 to get more stable results. And here we are running with replicate. So replicate is just what the name says. It's going to run this code chunk n many times, and the output will be just a vector. So we can get a tabular form of the vector by writing table attacks divided by the number of runs that we did. And we can see that we have only 4 solutions. And that surprised me a bit. I was actually thinking a little bit more about it. So we've only got 4 situations. Either the attacker loses all 3 dice. So the defender wins in all 3 cases. The attacker loses 1 die. And that is when, what's that situation? The attacker wins 1, the defender wins 2. The attacker wins 2, the defender wins. Oh no, that's not possible. So attacker wins 1, loses 2. And then the other way around, wins 2, loses 1, or wins all 3. So these are all the different solutions. And this is a frequency breakdown on how each one of these outcomes occurs in 100 replicates. So 34 times the attacker lost all 3, another 34 times the attacker lost 1, and then in the remaining 33 cases, the defender won more than the attacker. So at least here, we would estimate the probability that the attacker loses more dice than the defender as 0.68. So we just add up these two results. I've seen in the chat that there were a couple of other solutions. So I saw 62 a couple times. Which one is true, 68 or 62? Here we're just simulating. So we're not actually writing out all of the different solutions that could potentially happen. That would be the theoretical way to go. Here we're using R to quickly simulate 100 attacks for us. And I've used a seed of 2020 06 10 to so I use this seed. Whenever you use the same seed with the same code, you will get exactly the same results. Because here with sample, there's some randomness involved, or I should say pseudo randomness. If we set the seed, this pseudo randomness becomes deterministic. It just looks random, but we can reproduce the same results. And you can see that with the other way of rerunning the code looks a little bit different. Rerun is a functionality of per. Whichever functionality you prefer, as long as we use the same function for attack, we get the same results back after setting the seed. So 68% probability that the attacker loses more dice than the defender. So for me, I knew that in Risk it was quite scary to attack somebody, but I had not thought that it was that much in favor of the defender. And R taught me something. So sometimes we can use simulation to come up with these frequencies. How did that go? Too fast? Too little time? I think that you were just on the brink of getting results when the 10 minutes were up. So this is quite intricate. It took me at least 10 minutes to explain everything. Okay, so now I'm going to do something more so you can take a breather. Let's have a look at conditional probabilities. So here's an XKCD comic. It's unfortunately very relevant to Ames right now. So we're having a thunderstorm right on top of us in Ames, Iowa right now. And I'm usually not explaining jokes, but this joke is very relevant to conditional probability. So the idea of conditional probability is that we have an event A with a certain probability. And if we get additional information, the probability for this event A might change. So conditional on knowing the outcome of an event B, the probability for A might change. This is called the conditional probability of A given B. So B is given, we know B, and that might have an influence on our assessment for the probability of A. In math, we essentially restrict our sampling space from all of omega to just the elements in B. So we divide by the probability of B, and we only consider elements in B that are also in A, and that is going to be, so that's defined as the probability, as the conditional probability of A given B. So this is, if you think of B as the whole sampling space, so A given all of omega, this is 1, this is nothing but A. The conditional probability of A given the sampling space is nothing but the probability itself. So in a way, we've always been working with conditional probabilities. The idea now is that the additional information that we have allows us to restrict our sampling space. And that is going to, that might have an impact on our assessment of this event A. So let's come back to this comic. We have this piece of information. Probability to be killed by lightning is 1 in 7 million. I actually checked, and it's more like 1 in 12.5 million for last year. But that doesn't really matter for the joke. What is obvious here, if the probability to be killed by lightning, given to blindly rely on the statistic that it's very unlikely to be hit by lightning, even if lightning is currently happening, changes the probability to be killed by lightning in the first place. So here, XKCD makes it up as 1 in 6, and this is a joke. Just don't rely blindly on statistics. Seek shelter when there's a lightning, when there's a thunderstorm. But essentially, this is one piece or an example for a conditional probability. So, given that there's thunder and given that there's a thunderstorm right on top of us, the probability to be killed by lightning is probably higher than if there is not a cloud in the sky. Okay. So I'm wondering whether you're up for another your turn already. Let's go through this your turn together. So we've got a set of students here, 40 students in all. We know that all of them play at least one sports. So badminton, volleyball, or table tennis. And now we've got some additional information here about who plays what. And we can use this additional information to come up with these probabilities. So assuming a student is picked at random out of this group, what's the probability that he or she plays badminton or plays at least 2 sports? And then second, assume that we've picked a volleyball player so we've picked up a volleyball player. What's the probability now that he or she also plays badminton? What's the probability that they play at least 2 sports? So let's go through that. Essentially, we've got 3 events: badminton, volleyball, table tennis. We've got our sample space. You can think of a sample space right around that. And we already know that the sample space is this whole thing because all of the students that we're talking about play at least one of these sports. So 8 students play all 3 games. That's the intersection here. So let's put our 8 there. And now we just go through sequentially through all of the additional information that we're given. 10 students play badminton and table tennis. So that's an additional 2 beyond the 8 here. 20 students play table tennis and volleyball. That's over here. So that's 12 for this one. 12 students play badminton and volleyball. So we're just filling in all of those different areas in our so-called Venn diagram. 30 students play table tennis. That leaves 8 plus 12 plus 2. Overall, we've got 30, so that should be 8. Yeah, 8. 25 students play volleyball. There's 1 left who's not playing another sport. And then badminton, we're using the information at the top. Overall, we've got 40 students. So we're left with an additional 5 that didn't go in any of the other sets. So that's our base setup. And now we can assign probabilities based on randomly picking a student. So each student has the same probability to be picked, same chance to be picked. And we're going through our probability. So what's the probability that somebody plays badminton? We add all of the probabilities, we count the number of students in the event badminton. There's 19 of them divided by 40. So 19 out of 40, that's the probability that a randomly picked student plays badminton. Playing at least 2 sports is covered by this event here in the middle, this flower-shaped event. And we get 2 plus 8 plus 4 plus 12. So that's 26 students out of 40 play at least 2 sports. Those are our probabilities here. So now we assume that the student that we've picked is a volleyball player. So essentially what happens is we're restricting our sample space to just volleyball players. And now we're going through the same questions, answering the probability for badminton, given that we've got a volleyball player, is now 8 plus 4 out of 25, so 12 over 25. Playing at least 2 sports is everybody but this one, so 24 out of 25. So if we compare that to our previous results, probability of badminton is 19 out of 40. Probability of badminton, given it's a volleyball player, is 12 out of 25. They are really they are very similar. Playing at least 2 sports went up though from just over half, a good thing over a half really, to almost everybody. So there are situations in which this additional information doesn't change our assessment that much, like here with the badminton. Given a volleyball player, the probability to play badminton seems to be very similar. Playing 2 sports is changed a lot, given that we know that somebody already plays volleyball. So there's different effects. We can't say ahead of time how knowing an additional piece of information is going to change the probability of an event. So for that, we have a look at statistical independence. So statistical independence is defined as 2 events. When we have a look at the intersection, or the probability of their intersection. So probability of being both, picking an element that's both in A and B, that's equal to the probability of the product of their margins if these 2 events are independent. So that looks a little bit abstract, maybe. So if we think of this in terms of conditional probability and we apply the definition, then we can rephrase this conditional independence, then we can rephrase independence in terms of conditional probabilities as A and B are independent if the probability of A does not change given that we know the outcome for event B. So the probability of A given B is equal to the probability of A. So knowing B does not help us one little bit in terms of assessing the probability of A. So that's called statistical independence, or just independence. So events A and B are independent. So we'll come back to that. For right now, do you have any questions? I'll turn over to the chat and give you a couple minutes to ask questions.